5.2 notes, polynomials, linear factors, and zeros. Goal to be able to identify zeros of the function by factoring. You'll find that that looks familiar. We've done factoring. And using the zero product property and a graphing calculator, in our case, Desmos.com. You all have a laptop and have access to Desmos.com. Not everyone has access to a graphing calculator. So, example 1, we're going to write the polynomial in factored form. So first we could factor something out. What do they all have in common? X. So we factor out the x, and we're left with x squared minus 2x minus 15. And it is factored, but it is not fully factored. So we'll make our t-chart, put the c value here, negative 15. Remember, that's where we put the a times c. A is 1, so it's a level 1 factoring. And then what do we put on the right-hand side? Just b, yep, which is negative 2. And we have to think about what two numbers multiply to get negative 15 and add to get negative 2. 5 and 3. Which one should we make negative? The 5, good. And that adds up to negative 2. Great. So then we can leave the x on the outside and just write that as x minus 5, x plus 3. That's fully factored. B, what do those two have in common, Brooke? They both have an x. What else do they both have? 6. Factor out the 6x, we're left with minus 1. Good. And that is factored, but it is not fully factored. X squared minus 1 is of that special form, a squared minus b squared equals a plus b, a minus b. That is a special case that you learned about in Unit 4. So we can jump from this standard form of x squared minus 1 straight into its factored form based on that pattern. Example 2, finding the zeros of a polynomial function. So here's where we're finding the zeros. We found the zeros of quadratic functions. Do you remember that? We used 3 different methods, maybe 4. What was one of the methods we used for finding the zeros or solutions to a quadratic function? Quadratic formula. That was one of them. What else? Solve by factoring. Yep. Complete the square. And then there was the other one, which was solve using order of operations. When there was no b value, we could just solve using order of operations. So here there's a note, a super important note. The maximum number of zeros slash x-intercept slash roots. The maximum number of zeros is the same as the degree of the polynomial. I love that some of you are underlining and circling with me, because this is one of those things that as you go through your assignment slash your quiz on Friday or study for your test, this is a key thing to keep in mind. So when I had my y equals x squared parent function, the degree of this was 2. So the maximum number of times that this graph will hit the x-axis is 2 times. Remember that was the discriminant? And you'd find the value of the discriminant. So it could be where it hits 1 time, or 2 times, or 0 times. That's kind of what we've seen before already. Quadratic equation is a polynomial, degree 2. So we've got this equation here, and it's not in standard form, it's in factored form, which comes in handy when we're trying to find the zeros. It's really ideal. So to find the zeros when we're in factored form, we set it equal to 0. And we apply the zero product property, setting each factor equal to 0 and solving. So minus 2 on each side, x equals negative 2. There's one solution. X equals 1 is another solution. And x equals 3. So I'm going to go ahead and plot those on my graph. Negative 2 here, 1 here, 3 here. Right, it could go a lot of different directions from here, right? There's just a lot of different things that could happen. So it would be helpful to have this in standard form. The best way to do that would be to FOIL it all out, double FOIL it. But the most important things, we're just doing a sketch here, would be the lead coefficient and the C value. So to find the lead coefficient, we're just going to multiply the lead term in each factor. Yes, good. So our lead, sorry, not our lead coefficient, our lead term is x cubed when we multiply x times x times x. And then we're also going to want to know our constant term, which is also going to be our y-intercept. And to find that, we just multiply our last term. Since those are all constant values, so it works out nicely. We're going to multiply 2 times negative 1 times negative 3, which is 6. So I can plot that. Plot the 6, y-intercept. It's all about efficiency. Do as little as you need to do to make this work. Now let's go ahead and identify our end behavior. So our end behavior based on that lead term, it's odd and it's positive. So what would my end behavior look like? You can cheat and use your blue foldable if you want. Or maybe you remember. Down then up? Yep. Down then up. It ends on a positive note. It's odd. So it goes different directions. So from here, I'm going to go ahead and draw a little dashed line at each of my x-intercepts to kind of section off the different sections. And I know that it starts by going up. So I'm going to go ahead and just draw my graph moving in the upward, or sorry, it starts, the left end is going downwards. There, sorry, I said that wrong. The left end is going downward, and we're moving upward here, and we have to hit that y-intercept, and then we need to make a curve because we're coming down to hit that next x-intercept, which we would have to keep going down so then we could come back up to hit my final x-intercept and end on a positive note. I do want to write on here that this is a sketch. I shouldn't look at this and figure, oh, that's my relative minimum there, which we're going to define in a second. Because that could very well be down here, right? It's not exact. So now you can graph a polynomial. Isn't that great? It's exciting. But you also have a resource, which is called Desmos.com. Okay. Example number 3. What is a cubic polynomial function in standard form with zeros -2, 2, and 3? This should sound familiar from your semester exam. You had a question just like this. Here's your zeros. We could write the factored form just based on those zeros. If the 0 is -2, what would the factor be?
X minus 2?
Opposite.
Oh,
X plus 2. Okay, and just from the front, we just saw that if x plus 2 was the factor, the solution was -2. So x plus 2, and then x minus 2, and then x minus 3. So there's the factored form. We have the same pattern that we saw in part B on the front. We have this a plus b, a minus b situation going on, so we can jump to its simplified form. This will end up as the form x squared minus 4. Right? If this is a plus b, a minus b, then a squared would be x squared, b squared would be 4. And now you need to FOIL these two factors. So we go x squared times x is x cubed minus x squared times 3 minus 4 times x, and then -4 times -3 is 12. I check for like terms. Nope. Can't combine any like terms. So Autumn, what is my final polynomial? How would I read that? X cubed minus 3x squared minus 4x plus 12. What? Yep, that's how you read it. So there's your polynomial in standard form. What is a quartic? So that's a term that you had to make sense of. It means degree 4. Yes. Hopefully you had that in your notes on Monday. Yes. Okay. A little chart. So quartic polynomial function in standard form with these zeros. So go ahead and try and write that in its factored form. Start by writing it in its factored form. So we'll check x plus 2, x plus 2, x minus 2, x minus 3. You do the opposite. Any place you'd like to start, there's a lot of foiling that's about to happen. Yes, let's start there. We already know what that is. We just did that. It's x squared minus 4. So I can cancel that part out. I just essentially FOIL that. And then I need to take both of these factors one at a time. So we'll do times x plus 2 and distribute. X squared times x is x cubed. X squared times 2 is plus 2x squared minus 4x minus 8.
Why is the like x plus 2 and x minus 2, why is that minus 4? Why is that?
Because it follows this pattern of a plus b times a minus b, which always equals a squared minus b squared. The middle terms cancel out when you FOIL it. So, does that make sense?
Yeah.
Okay. So now you have that, but don't forget, I still need to multiply by x minus 3. I'm going to let you take a minute. Go ahead and distribute the x to each term. and then distribute the -3 to each term. Krista, I have your keychain. I don't know what happened. I tried printing 3 at once, and
It's okay.
this happened yours.
It's so
No, it's a special gift to you.
I appreciate it.
I'll print it again. I something is going on with my printer. The other two seem to be printing fine. Yes. Yes. Thanks. So we have distribute that x, so it's x to the 4th plus 2x to the 3rd minus 4x squared minus 8x. And then we distribute the -3, a little shortcut. I like to just line those up, so I'm going to put the minus 3x cubed right underneath my 2x cubed, because those will be like terms. And then minus 6x squared, and then plus 12x plus 24.
Yeah, I did this all wrong.
Sorry. So then when I combine my like terms, the 2x cubed and the minus 3x cubed ends up being a minus x cubed, a minus 1x cubed, or just minus x cubed. The negative 4x squared and the negative 6x squared end up as a negative 10x squared. The negative 8x and the 12x is a 4x. And then the plus 24. Raise your hand if you got that. A couple of you. Nice job.
I tried to do it all at once.
Ah, that doesn't work out. Now you know. All right, a few terms and then one more example. Multiplicity / multiple zeros. Multiplicity is a fancy way of saying the number of times a solution repeats itself. So let's take a look at an example first before you write down that definition. I have two negative 2's in the solution here, right? 2x plus 2's as the factors. So my solution, so the solution, -2, has multiplicity of 2, because it happens twice. It's a fancy word for saying how many times does that solution repeat itself. So you want to jot down that example. Two and 3 have multiplicity, I'm abbreviating, of 1, because they each only occur once. So let's write a definition here. Multiplicity / multiple zeros, the number of times a solution repeats itself. Relative minimum and relative maximum. You saw that in the roller coaster video? They said, here's maximum number 1, maximum number 2. So each maximum and each minimum, those are called relative, because it is the highest or lowest point on the graph within a certain region. So this would be, the relative minimum would be the lowest point on the graph within a specified region. Relative maximum, similarly, is the highest point. So you can see over here in the example, the highest point on this graph actually is infinity. It isn't a point. It just keeps going. And the lowest would be negative infinity. Right? It's not like a parabola where we have a very obvious maximum and a very obvious minimum. Okay? So whenever you have an odd degree polynomial, this will be the case. And it'll always have a relative max or min. So let's go ahead and, on Desmos.com, go ahead and type in this equation. And we're going to identify the relative maximum and the relative minimum. X cubed plus 3x squared plus 3x squared minus 24x. Alright, so you can zoom in, zoom out. Relative maximum, you could estimate, or you can actually click on it. And if you hover, it'll identify that point very specifically. So relative maximum is -4, 80. And just like with our parabolas, it really depends on the way the question is asked. Sometimes you just write 80. You just write the y value. And sometimes you write the entire ordered pair. What's the ordered pair for our relative minimum?
2, -28.
Good. 2, -28. And that's it. We talked about our relative max and min, our multiplicity, talked about converting from zeros into a standard form of a polynomial, talked about finding zeros and graphing, and factoring our polynomials.